So, now we will go further to the next crystal system, which is the monoclinic system. Monoclinic system, as we know, is associated with 3 point groups: 2, mirror and 2 by m. These are the 3 translation free point groups. Because of the fact that we have 3 dimensional periodicity, we get into the introduction of 2 other additional symmetry elements, which are the screw axis as well as the glide planes. So, we have to now consider the combination of the Bravais lattice with the presence of the two-fold and 2-1 screw, the mirror and also the associated glide planes. So, we will thereby generate several space groups. So, the first space group among these is the two-fold symmetry associated space group P2. And here what happens is that if you have an object which is xyz, which is sitting at point 1, it looks at and it undergoes a two-fold rotation. It goes from xyz to x bar y z bar. The location of the two-fold is now could be anywhere along the b direction. So, the value of the y is arbitrary. Whatever is the value of x and y, it will change to minus x minus z. But once we fix the value of y, then the value of y will remain unchanged. So, the location of the two-fold axis could be anywhere along this direction. As a result, we do not get any other positions associated in the b direction. Notice that this is a projection of OA looking down the c axis, and therefore, the angle between A and B is 90 degrees. So, this is a nice rectangle. You also notice that once we have this two-fold axis associated with the b direction, in the AC plane, particularly with respect to the A value which we have shown here in the projection, there will be an additional development of a two-fold axis at half position by definition. Any periodic repetition, as we have seen, will repeat its symmetry at half the distance, and therefore, we have this at half the distance. And this half the distance repetition will allow for the possibility of this point being related by a two-fold symmetry. So, it not only generates that point by the normal two-fold operation, the translation by 1 unit is generated here, and these 2 objects are related by the two-fold symmetry, and these are the 2 objects we will see in this space group, and therefore, this is z is equal to 2. And in this z equals 2, we can always have an object associated and sitting on the two-fold symmetry. Suppose you have a two-fold symmetry object, just like the pointer here, the laser pointer here, it has a two-fold symmetry. It is a circular point, so it has all kinds of symmetries. So, two-fold is also incorporated in the laser pointer. So, the laser pointer therefore has a two-fold symmetry, and suppose it sits anywhere along the length of this, you see that half the object on the top and half the object on the bottom are related by a two-fold symmetry. And as a consequence, this will be the special position in P2. And then we also have the possibility of the same special position coming at the repeat distance along the A direction. So, other than that, we have only the general positions x y z and x bar y z bar, and this generates 2 equivalent points, and the equivalent points on one translation take the objects outside of the unit cell, and so therefore, z is always 2 in an operation P2. Suppose we now want to consider this projection such that it is we show the AC projection. If we show the AC projection, you remember and you recollect that the two-fold axis now will be represented by a set of symbols which are now perpendicular to the 0 position, and that you should keep in mind. So, what is shown generally in all the projection diagrams, including the international tables for crystallography, unless otherwise specified, the projection is down x is A and down y is B, and C is coming either in a perpendicular or going inside the board in a perpendicular direction. So, it is not necessary in a case of a monoclinic system, it should come in a perpendicular direction. So, this angle is beta. So, the vector which comes out from the origin is at an angle of beta. So, it is not necessarily the value that it should be 90 degrees. So, that is a very important point. Do not think that this is now coming in the direction at 90 degrees. This comes at an angle of beta, and that therefore qualifies this complete description of this space group P2. The addition of a half translation is invoked in the case of a 2-1 screw axis. So, instead of a two-fold axis, if we have a 2-1 screw axis, then you see the operations very clearly that x, y, z now will undergo a mirror a two-fold operation, and after the two-fold operation you will see there is a half translation along the direction of rotation. So, in this particular case you have x, y, z, the rotation axis is y, and therefore the translation is along the y direction. So, x changes to minus x, y change, z changes to minus z. So, you generate this by two-fold symmetry operation plus a translation along the direction about which the axis operated, and so we get to this position. Now, this position on one translation will bring it down here, telling us that we do have a two-fold symmetry operation at half position, and these two now become the equivalent points in the unit cell corresponding to the coordinates x, y, z, x bar, half plus y, and z bar. Notice that we can also have the two-fold screw axis symmetry at 0 as well as 1. The presence of the translational periodicity has brought us the additional 2-1 screw axis, just like the logic we use for P2 and also to the triclinic system. So, these are the three simplest of the space groups we can discuss with respect to the equivalent points, with respect to special positions, and with respect to the generation of the equivalent points, and z is equal to 2, and if there is a object which has a two-fold symmetry, then z will be equal to 1. If there is an object which is in P2 1, then there will not be any special position, because the translation associated will destroy the possibility of having a special position. That means we cannot have this object, because this particular object cannot have a two-fold rotation followed by half translation within the rotation axis. That means if it is here and it goes there, you still have the 2-1 operation possible, but then the chances of such objects being in the P2-1 symmetry are very little. So, two-fold axis has a special position, 2-1 axis can also have a special position, I agree, but then we have to see it depends purely on the nature of the object. The object will not have its symmetry, which is now including the translational part of the unit cell, and therefore, the special position in P2-1 is not possible. We go further now. The possibility of now combining the presence of the second lattice which is available in a monoclinic symmetry, and that is the C-centered lattice. We saw the primitive lattice, the C-centered lattice. Now, we are looking at the possibility of the two-fold rotation being associated. So, we are going systematically. We are looking at the lattice symmetry first, then the lattice symmetry changes from P to C, then we look at individual point groups. So far, we have seen 2-1, 2-1 in case of the primitive lattice. Now, we see 2-1, 2-1 in case of the centered lattice. So, if we see the C2 symmetry that can be present in a monoclinic system, then what happens is that you now have the two-fold operation associated with the B direction, which will take the object 1 to object 2. Then the object 2, object 1 will also have the C-centered lattice. The moment we have the C-centered lattice, we generate this object at half plus x and half plus y, because it is C-centered. The moment we say C-centered, the x and y will be adding half and half. If we say A-centered, we will be adding y and z half and half. So, in this particular case of C-centering, we add half and half to x and y, and therefore, you have this equivalent point which is x, y, z. The x plus half, y plus half, z is an equivalent point that is generated by the lattice symmetry. This is not an equivalent point which is generated by the symmetry operation. So, the additional symmetry which we have got from the centering should also see the symmetry operation in order to be consistent with the definition of the space group. We have to have the closure property, and therefore, this point number 3 will also see the two-fold axis, which is now generated automatically at half position. Because we have a two-fold at 0, we have a two-fold at A, at half position we will generate another two-fold. So, this two-fold will take the object 3 onto object 4. Now, what is the relationship between object 1 and object 4? Object 1 and object 4 will have to now go in a very interesting way. I want you to find out what is the relationship between 1 and 4 and see and satisfy for yourself that a combined centering operation along with the two-fold operation will generate these 4 equivalent points. Now, having generated these 4 equivalent points, of course, this can be now translated by 1 unit. So, effectively these are the 4 equivalent points. So, 2 translated by 1 unit sees this particular two-fold axis, goes out of the unit cell, again this goes out of the unit cell and so on. So, inside the unit cell, if you count the number of objects, you will have 4 of them, qualifying itself to be the C2 axis. Now comes the possibility of C21. What happens when we get to a space group called C21? In the number of 230 space group list, C21 will not find its position. That is because we can always convert C21 to C2, and that is the operation which is shown here. So, first of all, let us look at how the C21 operation comes up. The C21 operation comes up from this point. You take this as XYZ, you rotate it by this is a 2-1 screw operation at the origin. If this 2-1 screw operation is at the origin, it is something similar to P21. So, you do the symmetry operation P21 and you get this half translated element, that when translated down by 1 unit you will get this element. So, these two now are related by a 2-1 screw symmetry. Other than that, we also have an additional point which will get generated due to C centering, and that comes up here with half plus x, half plus y, z. Now, these two objects are not directly related, but they are related through the operation of the two-fold symmetry, the 2-1 symmetry again. See, what is important here is to look at where the 2-1 symmetry positions are located. Suppose we take this as the origin, the 2-1 symmetry is located with respect to the 0 position here, and therefore, this now defines the unit cell OA. OA is the unit cell and OB is the unit cell that is associated with the C21 space group. Now, if we now consider the presence of the 2-1 screw axis, the 2-1 screw axis will appear again at half position. And so, this particular point which we see here now looks at the 2-1 screw axis here, and because of that presence of this 2-1 screw axis, this should undergo a 2-1 screw operation which will take it to this point. So, as far as C21 is concerned, 4 equivalent points get generated inside this outer unit cell. The outer unit cell, I mean the 0B 0A cell, the cell which I have marked by shown by the pointer. That is the unit cell that is corresponding to the presence of this C followed by 2-1 axis. Now, the fact that we have these 4 equivalent points inside this box does not qualify C21 to be a standalone space group, because what is happening is the presence of the 2-1 screw at this point and the 2-1 screw halfway and of course, the full way here, they are going to generate a perfect two-fold symmetry at 1/4. The reason why a perfect symmetry at 1/4 gets created is because of the centering. Because we centered at half and half, and then the corresponding 2-1 operation has taken place such that we also get the minus half kind of a situation where these 2 points are generated. The consequence of that is to generate, there is a, for example, if you look at these 2 points, you automatically see a two-fold axis between this and that. This is the xyz, you will see the corresponding minus xyz. and therefore this defines a two-fold axis. Now this two-fold axis, we are now taking this as the origin O prime. Therefore we have to add 1/4 unit to this one. The 1 unit translation will now be defining the A prime. The distance O prime A prime is same as distance OA, so there is no change in the A axis. Similarly, the O prime B prime is the same distance. The only thing that is changing here is the origin is shifting by 1/4. Once it shifts by 1/4, you see that the 2-1 axis is no longer in practice, but with respect to this O prime we have the two-fold axis. This therefore will generate another two-fold axis at 1 unit translation. It will also generate a two-fold axis at half point, which now relates these two. So if you now consider this unit cell, the O prime A prime, O prime B prime unit cell, let me mark that with the laser pointer, this unit cell, then you see there are again 1, 2, 3, 4 equivalent points in that unit cell. So I want you to write down the possible equivalent points for C21 and also the equivalent points of C2 and verify yourself that this can be now considered as C2, because it is just a question of shifting the position of the origin by 1/4 the unit. And it so happens that once it shifts by 1/4 the unit cell, the 2-1 screw is replaced by a two-fold axis. So C2 and C21 are one and the same. So the equivalent points will be exactly the same with respect to the C2. So we do not have a space group C21 anymore. So any combination of a C-centered lattice with a 2-1 is ruled out. That means when we go to the other space groups like C21 by M and possibly C21 upon C, which is the 2 by M operation, those two space groups will not be allowed. Not be allowed in the sense they are one and the same. So C2 and C21 are one and the same space groups. Now we go further. The two-fold operations are completed. So we have the two-fold symmetry, we have the P2 symmetry described, we have P21 described, we have C2 described, and we have shown C2 is equal to C21. And therefore the number of space groups are in monoclinic system so far are P2, P21 and C2 as far as the two-fold operations are concerned. Now we go to the mirror operation. The mirror operation, as we can see here from this diagram here, it is defining the space group PM. We can work out, of course, the corresponding equivalent points. I want you to write it down, and I thought of writing it down, but I think now you are experts enough to write down the equivalent points. So you have the origin here, and then you have A here and the B here. Where is the mirror located? The mirror is perpendicular to the B direction, and therefore you see that these lines are darker or higher width description of the black line. So effectively the mirrors are perpendicular to the axis direction. The two-fold axis is still along the B direction to define the minimum symmetry associated with the monoclinic system, and therefore we have a mirror plane where this now undergoes a mirror operation. So we have x, y, z and x, y bar z. Now once we have this generated, this can be translated inside the unit cell by 1 unit, and you see that automatically a mirror gets generated at half position, just like the two-fold axis and the 2-1 axis which we saw. And therefore we have mirror symmetries at these 3 positions, and this now generates 2 equivalent points, x, y, z and x, y bar z. And I want you to see that even though I have not written it, it can be considered as the equivalent points. The question is, suppose there is an object with a mirror, the object has a mirror in itself, would it generate a special position? This is something I want you to find out yourself. Having heard the argument so far, you have to find out whether the object can have a special position. If it has a mirror symmetry, can the object with the mirror symmetry be present on the mirror, in which case what would be the number of equivalent points. So this you can figure out yourself, it is not a very difficult proposition, and if the object lies on the mirror, what would be its coordinates? Suppose it lies at x equals 0, okay, and then obviously it is perpendicular to the B direction, and so it can lie anywhere in the plane of AC, and any point in the plane of AC, if it lies, would it be a special position? This is something which you figure out as we go to the next crystal system. The next crystal system is a sea glide that can be associated with the primitive lattice, as we discussed earlier. This is a consequence of the translational periodicity. So, again the diagram is fairly obvious here, even though I will go through the description for the completionist sake. You have the position x, y, z, and now what you do is you now operate the mirror symmetry. The mirror symmetry will take it to the other side, and then it will not keep quite there. It will either move along the which direction it will move. The direction in which it will move is given by half here. That means it is moving half the distance along the c direction, since this space group is PC. Suppose the space group is PA, then it will move half the distance along the A direction. And I want you to generate in your mind that diagram, that equivalent point diagram, where the space group is PA, which is also a possibility. The PC space group has the equivalent point where you generate the mirror and a half translation along the direction perpendicular to the mirror. In this particular case, it is perpendicular to the B direction. We can also move this in the plane of A and C, and if we move it in the plane of A and C along the diagonal, then it will become Pn, an n glide operation. So, I want you to put some thought into this, because there is no point in me telling all the space groups and all the way in which the equivalent points develop, but I want you to think about how Pn can be generated. And if this particular diagram I want you to generate for a Pn, maybe it will be given as an assignment later by our teaching assistants. So, find out what are the equivalent points if the space group is Pn. In this particular case, the space group now generates an equivalent point which is x, y bar half plus z. So, it is the translation is along the z direction, and that is why it is a sea glide. If the translation is along the A direction, you will have half plus x. So, this now generates again two equivalent points, and I want you to figure out whether this has any special positions, PC. Next we go to the mirror symmetry, but now we will change the lattice type, and we will change the lattice type to C. So, now it is a C centered lattice in a monoclinic system. That means for every point x, y, z, you have a point at half plus x, half plus y, z. So, if your object is up here, you have a corresponding point which will correspond to x plus half, y plus half, z, which is shown as number 3 here. So, 1 and 3 are related due to the presence of the C centering, and now of course, the mirror operates. The mirror operation will take this point onto 2, the simple mirror operation, and this now point also will add half and half. So, you will get this point, and you see that there is a mirror which is automatically generated in the middle. So, if there is a mirror, the mirror operation associated with 0, you will have mirror at half, you will have mirror at full length. Now, where is the C glide located, C centering located? The C centering is located at this point, half plus x, half plus y, z. As a consequence, if you now examine the equivalent points 1 and 4, you find a relationship between them. The relationship tells you that there is a glide plane which is present at 1/4 the position. It is not in the space group. The glide plane is a consequence of the centering. Because we have the centering, the x, y, z is becoming half plus y x, half plus y and z. That presence of the half plus x, half plus y, z and the corresponding mirror operation relates 1 and 4 by a C glide operation. So, if you examine 1 and 4, you see that it is a C glide. And this particular glide operation, is it a C glide or an A glide? You look at these equivalent points and see whether it is a C glide or an A glide. It is an A glide, because the glide operation is adding half to the value of x, and this is coming as a consequence of the presence of the mirror symmetry, which now takes the C centered object operates the mirror, and therefore you will get a centered lattice associated with this. Of course, the presence of the mirror is half distance, and you see that half distance mirror is shown by a dark line here, and therefore you have the mirror at once you have the mirror at 0, you have the mirror at half, you have the mirror full length, and you develop a glide which is an A glide here. In the case of the C centered lattice with a mirror symmetry, you invoke the presence of an automatically available A glide. Even though it is a part and parcel, it is not a part and parcel of the description of the space group, because the description of the space group, the dominance is given to the C centering lattice. So, the lattice gets the highest priority, and then it generates the equivalent points corresponding to the lattice, and then the symmetry operation takes over. So, the presence of the C centering therefore has given rise to a possibility of a glide plane which is at 1/4 this distance. So, at 1/4 this position you will get an equivalent point. So, this brings us to the fact that given the positions of the symmetry elements, given the positions, these positions of the objects, we can derive the symmetry points, symmetry equivalents. That means, if this is the point x, y, z, we can derive the position of the symmetry position here by looking at the symmetry operations that are possible. One is, now we took this point 1, took it on to the point 3, operated the mirror plane. So, we got this. So, if that is how we can generate x, y, z, and x plus half, y bar plus half, and z. Now, we see that these two are related by a C glide, A glide. So, what it essentially tells us is that given the diagram like this, it should be possible to find out the equivalent points. The other issue is, given the equivalent points like this, it should be possible for us to find the space group. And if we find the space group, we should be able to generate the symmetry operation diagram. This is known as the symmetry operation diagram, along with the objects which are shown here, but you can replace the objects, and in international tables what is given is the objects are separately given in one side, and the symmetry operations alone are given on the other side. We will get a look at it after we finish this discussion, so that we understand the operations of the symmetry elements and also the presence of the centering of the lattice. And later when we go to the space groups, we will see that the international tables for crystallography, which is an enormous effort put by early day crystallographers, and eventually now it is undergoing recent changes, it is available online, and one can actually look at two possible diagrams, one diagram corresponding only to the symmetry positions, the other diagram related the objects. So, that this complexity that is associated, if you think there is a complexity associated with this, I do not think there is any complexity anymore associated with this, because you have just now understood the entire diagram. You have not only just understood where the objects are coming and how they are coming, you also have understood how the symmetry elements are located with respect to the space group. Having seen that, I have given you the CC diagram. So, the CC diagram now is the C centered lattice with a C glide. Now, it can also be CA, because A and C are interchangeable in a monoclinic system, because A is not equal to B, not equal to C, and the two angles which are at 90 degrees, which is essentially considering B as the unique axis, will allow us to have either A or C. So, we can have a CA or a CC, both space groups are possible, and here the diagram of CC is given. Now, it means that we have a C centered lattice with a C glide associated with a C glide. I want you to think whether CB is possible. CB, that means the B glide which is along the B axis. There is no possibility of a B glide along the B axis, because in a monoclinic system B is given always to the two-fold unique axis. Since the B is given to the two-fold unique axis, it is not possible to have CB. So, CC and CA are both possibilities. And in the case of CA, what we see here is that the object 1 now sees the C glide perpendicular to the B axis. So, the C glide perpendicular to the B axis is indicated here, and so we generate these two equivalent points. So, 1 and 2 will be generated by the operation of the C glide. Now, we also have the C centered lattice. The C centered lattice will generate point 1 and point 3, same logic as we used in the case of CM. Using the same logic as we used here, we generate 1 and 3 by C centered lattice. 2 and 4 are the operations due to the C glide. Now, C glide being at 0 will automatically generate 1 at half position because of translational periodicity, and we have this as well. So, we can now bring all 4 points inside the unit cell. I want you to write down the equivalent points. This is a home exercise. I want you to write down what is the value of 1, what is the value of 2 in terms of x, y, z and this kind of equivalences, which we have shown in case of CM. Modify the CM equivalences to generate CC. It is not a fairly difficult job, it is a very straightforward job. So, you should be able to do that. Once you do that, you will see something very interesting, just like what happened here. In case of the mirror symmetry, we developed a C glide at 1/4. Remember A glide at 1/4 this position. Now, what will happen is, because of the operation of the C centered as well as the C glide, you will generate an N glide at 1/4. I want you to find out how this N glide operation has come and write down those equivalent points as well, which will be the same as the equivalent points that is allowed by CC. So, at this time we will just consolidate the diagram here. We did, in fact, we started from the two-fold symmetry, and then we went to the presence of the mirror symmetry, the second symmetry operation in a monoclinic system, and we then looked at the possibility of having the C glide associated with the primitive lattice. Then we brought in the C centering, which essentially is operating on the mirror symmetry. We find an appearance of an additional symmetry element, which is not a part and parcel of this CM, but indeed it, in some sense it is a part and parcel of this, because of the fact that we C centering takes x, y, z onto half plus x, half plus y, z equivalence, and as a consequence of that we develop the A glide, which is at 1/4 the position. And if we look at this situation where we have a C centered lattice with a C glide, then we generate equivalent points which will result in the presence of an N glide, which is at 1/4 and 3/4. So, more additional symmetry elements start cropping up depending upon how we combine now the lattice symmetry with the point group symmetry. So, the flexibility that is allowed now for the objects which go into these exposed groups kind of restricted, because it has to satisfy the other symmetry elements which are also developing. For example, in the case of the CM symmetry, you had the mirror, you want to you get a glide. So, the equivalent points which we generate will have to also satisfy the A glide condition, and therefore the object is now arrested. It is like, putting all of you into a classroom and making you sit in your respective chairs. So, it is essentially restricted by the additional symmetries. So, CC will also generate additional symmetry, the N glide, and therefore there are more restrictions on CC. Now, you can think of the situation when molecules crystallize in these kind of space groups. The molecules, when they crystallize in these kind of space groups, will have to satisfy all the symmetries which are also coming in addition to the existing symmetry in the point group and the lattice type combination, and thereby they are restricted to those places. And these restrictions will therefore tell us which compound can go into which space group. This leads us to the possibility whether we can a priori predict a crystal structure. A priori prediction of the crystal structure is also a possibility. But whether we can unconventionally or unequivocally determine the space group is an issue. This is something we will discuss when we talk about crystal structure prediction. It is not a straightforward way in which we can predict the crystal structure. Otherwise, we will not be taking this course and doing X-ray diffraction experiments to find out where the atoms are, because the moment we see the object, if we can predict which space group it goes into, the job is all done. So, the solid will be described fully.